All right, that brings us to our research book, chapter 10, which is clarifying measurement and data collection in quantitative research, which, if you recall, quantitative research typically involves studies with numbers and quantifiable data. So measurement is just the process of assigning numbers or values to concepts, objects, people, event, whatever it is you're studying. Direct measures are determining the value of a concrete factor. So that's like weight or blood pressure. And then indirect measures, or sometimes called indicators, capture the elements within an abstract idea. So pain is a good example of that. So the level of measurements are the rules for assigning numbers to create a hierarchy. So for example, on this pain scale here, we can ask about pain reduction. We can ask that 0 to 10 scale. That's a quantifiable piece of data. But what we really need is the larger proportion of things that are related to pain. So what have we done to reduce pain? How is quality of life affected by pain? So you can see here that indirect measures capture an element within an abstract plan. We can't really measure pain specifically and all of the things that are related to it. So nominal level measurements are used when data can be organized into category but not rank order. They differ in quality, not quantity. So the items must fit into one category or another. They can't fit into both. So for example, if you are married, widowed, single, or divorced, you maybe could be divorced previously, but now you're married again. The answer is you're married, because you can't have both. So there has to be an exhaustive list. And then ordinal level measurements is data that's assigned to categories that can be ranked. So just like in nominal level measurements, those categories do have to be exclusive, but this often uses scales. So for example, if I scored myself a 0, I would not have any shortness of breath, and a 1 would be minimal shortness of breath, and a 2 is moderate, and so on. Interval level measurements use scales with an equal distance between them. So they represent a continuum of values that must be exhaustive and exclusive, and ranked. So temperature is a good example of this. We can start out at 0 and maybe 10 degrees, 20 degrees, 30 degrees. That would be an interval level measurement because there's 10 degrees between each of those measurement scales. Then we get ratio level measurement, which is the highest form of measurement, and it meets all of the rules. So it's got to be exclusive, exhaustive, ordered, equally spaced, and there needs to be a continuum of values. So they can be added or subtracted or multiplied and etc. And the final rule here is that there has to be an absolute 0. So for example, when a baby is born, it can't weigh -2. There has to be an absolute 0 there. But we would have to go up by the same scale in order for that to be a ratio level measurement. So an ideal measurement is a true measurement, but some error is always present no matter what you do. Maybe the scale's inaccurate. Maybe the person doing the measuring isn't doing it quite right. Indirect measurements are abstract. So random errors are the difference between the true value and the measured value at random. There's no pattern in the error, and you can see that down here. This is random error. We don't really have a rhyme or reason as to how it's happening. It's just plain wrong. Maybe 4 different people are taking data and 2 of them are doing something over here, and one of them just writes a number down wrong, and then one of them accidentally puts a little extra weight on the scale when they take the measurement. So it's just a random error. A systematic measurement in the error is always off in the same direction, and it's usually due to the same cause. So for example, if the person is under the impression that they're supposed to have the participant leave their shoes on when they measure their weight, then every single one of those weights is going to be off by a little bit, just based on how heavy that person's shoes are. So the other thing is we have a scale that doesn't quite meet the specificity, oh my goodness, enough. So maybe we're measuring hope on a scale, right? That's a difficult thing to measure. But what we also really get is responses for social support. So maybe what we've learned here is there is a correlation between hope and social support, but we weren't measuring social support, we were trying to measure hope. So it usually means the scale isn't specific enough. And then there's reliability. So that's the consistency of the measurement method. So if in the beginning the scientist is super careful and measures down to 1/4 of an inch on every single patient, and then by the end they get sloppy and they're measuring a 1/2 inch or a full inch off, then the consistency is incorrect. It should produce similar scores every time the subject takes the test in a brief period. Now, scores on a lot of these tests will change over time. That's just the nature of whatever it is you're studying. But you should be able to take the same test every 5 minutes 3 times in a row and get about the same answers, because other than maybe your frustration level with the test, nothing has changed in that amount of time. Reliability tests determine the measurement error of a scale, and those results are specific to the sample being tested. So internal consistency is getting the same results within the same scale when the questions are asked differently. You guys have all taken scales like that. That's one, for example, when we take the trust survey. There is a number of questions that ask, do you trust your leader? And then it will ask the question in a different way and say, do you mistrust your leader? So it's asking for the same results, but it's asking it in a different way. That's internal consistency. Stability and reliability is the reproducibility of the scores. So that's determined using a test-retest reliability. And then equivalence is comparison of 2 versions of the same instrument or 2 observers. So the way that I observe something and score something is going to be different than the next clinical instructor, for example. So inter-rater reliability is the ability of more than one observer to mark the same responses. So if you have 2 people performing tests during a study, you want both of them to perform those tests in exactly the same way. So a good example of that is the NIH score. So it has to be done in a very particular fashion, or else we don't have inter-rater reliability, and therefore the test isn't a reliable method to decide how, how the stroke is or if it's improving. So alternate forms of reliability means we use 2 different test methods, but we get the same result. So maybe I did a verbal survey over the phone, and maybe the other person did a computer survey. We should get the same results out of those 2. Validity is another complicated thing. This seems complicated, but it kind of makes sense if you think about it, so stick with me. Content validity is the extent to which the measurement contains all major elements that need to be measured. Okay? We can have the best study in the world, but if it isn't measuring what it's supposed to, we don't have content validity. Construct validity does the measurement actually measure what it's supposed to. So if we can go back to the hope example. If we're trying to measure hope, but what we're really getting is social support, then we're not getting construct validity. Convergent means 2 scales measuring the same content are delivered at the same time. And if that's the case, they should be positively correlated, right? So if the scales are convergent, that means they both should be headed in the same direction. Divergent are 2 scales that measure opposite things, and they should be negatively correlated. So if I'm measuring hope and hopelessness, then one should be higher and the other should be lower. If I'm measuring hope and hope, they both should go the same direction if the scale is working correctly. So just a reminder, and here's that bullseye example again. If it's both reliable and valid, that's a bullseye. That means we hit the middle of what we're trying to get. This one's not reliable or valid, okay? It's not all over the place, and it's all kind of in one direction, and it's also not on the bullseye. Low validity and low reliability means it's everywhere. It's all over the place. It's not asking the right things, we're not getting the right responses, we're not getting it consistently, it's just random. And then if it's reliable, but not valid, it means we're getting the same answers over and over again, but we're not getting the answers we actually want. Then it comes down to readability. None of this matters at all if the participants in your study aren't able to comprehend the content or the scale of the study. So this is actually from 2003, but I'll tell you with Facebook it hasn't improved much. The portrait of adult literacy in America is actually pretty low. About 14% of us are only able to do very simple literacy activities. This does not involve fact-finding on Facebook. About 29% of us can do very simple things like pamphlets, very easy to read, like 9th grade style literature, stuff like that. And then about 44% of us are okay. We're looking through references, we're able to look up sources, we're able to determine information, and then actually a very small percentage of us are actually capable of comparing things like 2 different editorials and determining what the difference is between the 2. So you have to base your study based on what your study participants are going to be able to do. You would never create a study asking 2 preschoolers to compare, one paragraph versus another. the preschoolers can't read the paragraph, the study is null and void. The same thing is true in a larger extent with our patients. We can't ask them to go home and understand what their disease process is if their learning level, we taught them at a 9th grade level, but they're really at a 6th grade level. So we have to kind of look at that when we are talking about creating our study materials. That brings us to physiological measures, which quantify the level of functioning in the human body. These are things like blood pressure, heart rate, BMI, any kind of physical monitoring. So that brings accuracy into the picture. How well does it actually measure the biomarker? So for example, we have a pulse ox that does an okay job of noting our oxygen saturation, but not nearly as good of a job as an arterial line would, right? So the arterial line is more accurate than the pulse ox, but the pulse ox is cheaper and easier to read. The precision is the degree of consistency or reproducibility of measurements. So for example, back in the day when we had POC troponins, we had a difference in the measurement scale between the POC troponins and the lab-drawn troponins. If you're looking for precision, but you're comparing a POC troponin versus a lab-drawn troponin, you're not going to get the exact need that you are looking for. And we also have a variety of errors, and for most physiological errors, those include things like in the environment, the user itself screws something up, your equipment fails, or even your interpretation. If you look at, for example, incoming EMS STEMI patients, the interpretation of those results from the EMS may be different than the interpretation of the ER physician, which may be different than the interpretation of the cardiologist. We also want to take into account the quality of the diagnostic test. So that's the accuracy. If it's accurate, it confirms the diagnosis. Tests the presence or absence of a disease. So do you have it? Do you not? The criterion standard is the most accurate means of currently diagnosing. So that's evidence-based practice. If we know the most accurate way of diagnosing a blood clot is to do a nuke med scan, then that's what our first priority should be in diagnostics. We don't usually start there though, right? We usually start with maybe a chest x-ray to rule out a lung disease. And then we'll do a D-dimer, and then we rule in those diagnostic tests. So the criterion standard is just the gold standard of those tests. So screening tests, and you guys have gone through this in your statistics classes already, so I'm going to kind of breeze over it, have true positives, meaning we said they have the disease and they have their disease. False positives, saying they don't actually have the disease, but we said that they did. False negatives, meaning they actually do have the disease and we said they didn't. And true negatives, meaning we said they don't and they don't have the disease. So sensitivity is a true positive rate and specificity is a true negative rate. That also brings us to likelihood ratios, and that helps researchers determine the accuracy of diagnostic or screening tests. The ratio of a true positive versus a false positive is called a positive LR, and a true negative versus a false positive is a negative LR. And this is just a little chart over here that kind of tells you the math behind that. You're not going to need to understand or to do the math behind it. I just want you to know what it means if you come across it in your research. Then we get to observational measurements. So that's the interaction between study participants and observers. So unstructured observation is just spontaneously observing and recording in words. Structured observation occurs when the researcher defines what's going to be observed exactly, and then those observations are recorded and they're usually coded as numbers. So it's a little bit more scientific. We can do a lot of different types of data collection. We can use interviews, which is just, that verbal communication between the researcher and the participant. Those are usually unstructured and conversational, or possibly structured. And when we start to structure them, they turn into a little bit more of like a questionnaire or a survey. So a questionnaire is just that self-report designed to find the right information. So people are very cautious about how they write questions to make sure that they're getting the right responses. It's useful for gathering a broad spectrum of information. It can be open-ended and closed-ended. Of course, if you recall, closed-ended questions are a no, yes, no answer. My age is this, my sex is this. Open-ended questions are how do you feel about? Describe to me a time when. Those are the open and closed-ended variations. Participants often don't fill out the whole survey though. Think about how many times you were asked to complete a survey on something you purchased or something, service that you've gotten from somebody. How often do we actually go through and fill out every single one of those questions? So that actually can cause us some validity issues because we start to see some bias. We also have scales, which is a self-report measuring phenomenon that answer then questions. So rating scales, of course, are ordered list with a number assigned to each category. So we see that in our pain scale. And then, of course, we have Likert scales, and that determines attitudes or opinions. So this is an example of a Likert scale, somebody who's not at all satisfied towards somebody who's extremely satisfied. And Likert scales are one of the most commonly used type of data collections around. Visual analog scales are also very similar, and you can see here we can kind of see visually, even though we've assigned a number to it, if we didn't understand numbers or we didn't understand the language or we're too young, we could also verify using a visual scale. So the data collection process is finding study participants and collecting data. Recruitment's going to depend on the type of study that you're trying to complete. Data consistency is key to a good study, and then control is important in some types of studies. That's it for this chapter. If you have any questions, let me know.